Yeah, camps on everyone. Let's start off. Yeah, camps on.
Camps on.
Able to hear me clearly, right? Yeah. So I'm traveling a bit, so maybe there might be a little lag. If there's any question or query, right, I won't be able to see your messages. So please unmute and ask. But is my voice clear? You can just nod your head. I can see you guys still. But great. Okay, let's start off then. Today there'll be no break. We'll wrap up also a little early. So let's see. So last thing that we did was speed of sound, classless correction and everything. Right. Let's start off with a question. So we have a mixture of gases, oxygen and helium. 3 moles of oxygen and 2 moles of helium are mixed at 500 Kelvin. Find speed of sound and find VRMS. Hope you remember what is RMS, root mean square velocity, which we did in KTG. Let's see how to do this. Try, I'll give you 2 minutes. Numbers are bad. Sound is fine. I'm more interested in the VRMS. Let's say the speed of sound is root over gamma mixture RT by M. . 。 So F of the mixture will be N1 F1. So that will be 3 into diatomic is 5 plus 2 into helium is 3. 3 plus 2. 21 by 5. And gamma is 31 by 21. There, you can put down all the numbers, you'll get the answer. This was easy. Straightforward substitution. What about RMS? Now listen carefully. RMS is a little different. Now let's go back to the definition of VRMS. If you remember, VRMS square is simply if you have n molecules, V1 square, V2 square, so on till Vn square by n. This is the formula for RMS. Sigma V square by n. Now when you take for a mixture, now see in the mixture we have two different molecules. So if you take V1 square, V2 square, so on till Vn square, let's say this is for oxygen. V1 dash square, V2 dash square, and so on till Vn dash square. Let's say this is for helium. Because understand the meaning of VRMS. It is a total root mean square. So take all the speeds ka square and then it will be 1 plus 2 plus so on till n plus 1 plus 2 plus so on till n dash. Isn't this the formula for VRMS? You see, VRMS doesn't care whether it is monatomic or diatomic, isn't it? It is simply the translation thing. Now, if you look at this, so this is sigma V square for oxygen plus sigma V square for helium, sigma n for oxygen plus sigma n for helium. Is that right? And we know if you take VRMS for oxygen, that will be sigma V square for oxygen molecule, sigma n of. So if you replace sigma VO end up with sigma NO2 VRMS square for oxygen plus sigma NO and helium. Yeah. So if I just combine the whole thing, this will be a general formula. So VRMS square for a mixture. So these are the total number of molecules I can divide by Avogadro number. It becomes the moles. So this will become N1 V1 RMS square N2 V2 RMS square by N1 plus N2. This is your general formula for RMS. the most common mistake what people generally we do, right, is this: we take VRMS square for a mixture is root over, remember, 3RT by molecular weight of a mixture. This is wrong. That doesn't work. Getting it? So what is the VRMS for our question now? 3 moles of oxygen का RMS value, 2 moles of helium का RMS value, and what is the oxygen का RMS? Root over 3RT by 32 into 10 power minus 3. What is the helium का RMS value? Root over 3RT by 4 into 10 power minus 3. Take them and substitute this. Is this making sense, everyone? Clear with this? No. Just try to see how different are both the formulas. So this thing which we got VRMS square, if you put N1, what is this RMS here? 3RT by molecular weight M1 into 3RT by molecular weight M2 by N1 plus N2. You just take out 3RT common. You actually get N1, M2 plus N2, M1 by M1, M2, N1 plus N2. Right? This doesn't look like 3RT. If you take average molecular weight, that will be N1, M1, N2, M2 by N1 plus N2. Can you see? They don't look the same. You cannot use average molecular weight for a mixture. So that is a catch. For sound, you can use. Because if you go back to the derivation of speed of sound, how did we derive it? We said PV per gamma. Now gamma is for a mixture. And that same gamma went on replicating. And when you used PV is equal to nRT, that N is the total number of moles. Clear with us? So it kind of worked out there. So be careful with this. Any doubt on this? Clear, na? Ansh, Devansh? Vihan, Saish, clear with this? Let's see one more. This is x is equal to 0. This is x is equal to 100 meters. Here temperature is 100 Kelvin. Here temperature is 300 Kelvin. This whole space is filled with helium gas. So here the temperature is not constant, it is changing linearly from 0 to 100. It's going from 100 to 300. Find the time taken for the sound to travel from 0 to 100. Again, you can clearly see the speed is not constant. The more you travel, the more the temperature rises. So let's get this. I'll give 3 minutes. I won't be able to I won't be able to see your answers. So for today, it's okay if you don't type. But if there are any questions you didn't understand anything, please unmute and ask. What's the first thing? Temperature varies linearly. Can you find the relation between T and X? Start from there. Let's see. First, let's get the linear function. So temperature varies linearly. So T is equal to Ax plus B. डालूं गर्म पानी at x is equal to 100 yeah, my friend has already ordered. Yeah. So this will be 300 into 100 plus B. This comes out to be 2. So temperature is 2 into x plus 100. Got this? That is the easiest one. Now, if you look at the velocity of sound, this is gamma RT by M. Gamma is 1 plus 2 by 3. M is 4 into 10 power minus 3. Now, when you substitute here, you will see something interesting. V sound square, gamma R by M, 2x plus 50. This would be 100 gamma R by molecular weight plus 2 gamma R by M into X. Can you see something? V square, U square, 2AS. You get a constant acceleration. Or you can integrate. If you didn't figure that out, you can always integrate dx by dt and get it. So your initial speed is root over 100 gamma R by M. So this sound actually travels with a constant acceleration, which is gamma R by M. Then I can use S is equal to ut plus half at square. This S is 100 meters. You get a quadratic. Solve this, you'll get time from here. Makes sense. A better question would be this. What if I send another sound wave from here? Find the point where the sound waves meet. That would have been interesting. So basically, this guy will decelerate and this guy will accelerate. Can you see some difference? This thing looks like that string question, na? String hanging from a ceiling. There also, if you observe, tension was changing linearly. So it's the same thing. We just made it for sound with the temperature. Clear with this? Any doubt on this? Great. Next one. Now, if you have speed and you have pressure and stuff, then we have intensity also.
Sir, I have a doubt in this question.
Which one?
The 33rd one. Yes, sir. So if we solve the quadratic for t, we'll get two functions of two
एक
values
नेगेटिव
of
आएगा रे.
time. अच्छा, okay.
एक नेगेटिव आएगा, I guess.
Okay.
The reason you'll get two values of time, but that would not make sense, na? Negative भी क्यों आएगा? Negative, you will get one negative that is there. Negative meaning it's past time. तो नहीं है. नहीं, you will get two times. नहीं. I think it is this one, Rehansh. We said sound starting from here, na? We didn't say which way, right? So if you had sent sound this way, this would travel and come back like this. Ansh,
Okay, sir.
I think that was the second route, I guess.
But there's no reflection medium on the left side, right? So
No, it doesn't make sense. Max doesn't care na what is sound and all. हमने equation बना लिया. What is the equation? Particle starting here with speed u. Time taken to reach here. Now that u can be positive or negative.
so it will go somewhere to the left and then turn and then come.
मतलब Max is assuming like that.
अच्छा, okay.
But we know it doesn't make sense.
Right.
So I think something like that is happening. Max का problem वही है ना. It doesn't know what we are talking about. It will give you the roots. Now, if you see the intensity of sound, we have derived these formulas in waves on a string. We can use the same formula, half rho a square omega square v wave. The only thing you have to be careful, v wave is not root t by mu anymore. V wave is root over bulk modulus by rho. and delta P max is BAK. So these are the three important formulas, everyone, in sound waves. They actually manipulate these three equations and they create all other stuff. The problem with this formula, right? Studying intensity of sound with this formula is not really convenient. The numbers are pretty bad. So we prefer to study in something called decibels. We'll use a symbol beta. So this decibels is actually a log scale. So beta is given by 10 log intensity by I naught. Where I is the intensity of the sound. I naught is a constant which is 10 power minus 12 watt per meter square. So decibels is a log scale, and this log scale have a problem. These things can be quite deceptive if you really don't understand what you're talking about. The first time I think you learned a log scale in 11th and 12th is in chemistry. Remember pH acid? So pH is actually a log scale. So if someone tells you I have an acid of pH 3 and pH 6, can you tell me how strong is pH 3 compared to 6? It's not double. If you look at pH scale, it is 10 log H plus concentration. So this is 10 power minus 3 and this is 10 power minus 6. This is 1000 times stronger, isn't it? A pH 3 is 1000 times stronger than a pH 6. But it's misleading. The 3 and 6 will make you feel like, oh, it just doubled, but it's not that way. So similarly here, decibels is also log scale. It is pretty misleading. So if you double the intensity, then what happens? If intensity doubles, 2I by I naught, we get 10 log 2. This will be your old beta. So the difference is 10 log 2, which is approximately 3 decibels. Understand the implication of it. If someone comes and tells you my intensity has gone from 50 decibels to 59 decibels, people will think, oh, sirf 9 hi bada, right? And it looks like 20%. It's not. 50 to 53, it doubled. 53 to 56, it doubled. 56 to 50, it doubled. It's 2 into 2 into 2, it's 8 times. You get anything? So decibels can be pretty misleading. So if intensity doubles, the change in decibels is 3. So for every 3 decibels, approximately it doubles. Now this will be good theoretical questions. Matlab, if intensity becomes 10 times, that's a difference of 10 decibels. So in change in decibels is 10. So for every 10 decibels, your intensity becomes 10 times. So there was a question like this one in some PYQ or some CET or bits. Let's say 50 decibels, the intensity is high. If the sound becomes 100 decibels, then what will be the intensity? If intensity I gives you 50 decibels, then for 100 decibels, what should be the intensity? What do you guys think? It will become 10 power 5. Because if for every 10 decibels, it becomes 10 times. So 50 to 60, 10. 60 to 70, 10. 10, 10. There are 5 tens. So 10 into 10 into 10. And actual intensity becomes 1 lakh times. Clear with this, everyone? Clear? Next time. Let's see a question based on this. So we have a point source here. So here sound travels in spherical wavefronts. We have 2 points here, A and B. RA is R and RB is 2R. Second case, we have a line source. So here sound travels in cylindrical wavefronts. We will talk about this in wave optics. If you think about this, this kind of looks like, field due to a point charge and field due to an infinite line charge. Isn't it? If you take a point charge, how are the equipotential surfaces? Shells. If you take a line charge, how are the equipotential surfaces? Cylinders. Same thing. Find the difference in decibels between A and B. Both the questions. This is how they'll frame a question. Let's get this. What's the catch? See, first let's define what is intensity. The intensity is simply power by area in which power transmits. So in case A, intensity will be power by 4 pi r square because the area is going in spherical wavefronts. So intensity at A by intensity at B will be 2 r square by r square 4 is to 1. And we saw for every time you double, there are 3 decibels ka difference. So beta A minus beta B will be approximately 6 decibels. Whereas in the second case, it's a cylindrical wavefront, so P by 2 pi RL. This is 1 by R. If you actually think about this, doesn't this look like a point charge ka field? What is the point charge ka field? KQ by R square. What is an infinite line charge ka field? 2k lambda by R. Can you see the resemblance? So here IA by IB will be 2 is to 1. So here the decibels will be beta A minus beta B will be 3 decibels. There, that is how they'll play around with this. So depending on what kind of source you're using, the whole answer will change. And more about this wavefront we will discuss in next chapter, wave optics. But this much idea you should have. You might be thinking, how does a cylindrical wavefront looks like? Ever been to a water park? Did you see they send a waves in a water park? If you ever seen that when you're in that big pool, wave pool, and they send a wave, the wave actually kind of comes like this, right? Like a cylinder. If this is your water, this whole thing is like a cylinder. The water just comes like a cylindrical wave. Or when you go to a beach, you can see it's kind of like a cylinder when it is far. Clear with this? So in this case, energy will be 1 by R function. Generally, that is how they play with intensity. They play with decibels and all that stuff. So this is all one part. Sound waves ka equation, relation between linear displacement and pressure. And then we had speed of sound, longitudinal wave, transverse wave, all these things. The next thing, stationary waves. Like I said, in this entire chapter, the stationary waves is the most important one. We did stationary waves in a string. Now we are doing stationary waves in sound. So if you remember, there the equipment ka name is sonometer. Here the equipment name is organ pipes. So what are these organ pipes? These are actually thin hollow pipes. So whenever you think of them, the best way to think of a flute. Flute is an organ pipe. So when you blow air into that and you have different holes, and when you change the holes position, you're changing the length of the thing. And this is what I said last time. Every musical instrument is based on sonometer. Stringed instruments are based on sonometer. Tabla, flute, these things are based on organ pipes. The concepts will be same. right? The only difference is in strings we study displacement, here we study pressure. So in this, the first possibility is an open organ pipe. So basically both sides it is open. So these open ends are actually pressure nodes. What do you mean by pressure node? Again, understand what is a node. In a waves on a string, we said node is a point which does not move. The actual definition is this: node is a point where the property doesn't change, isn't it? In waves, that y is not the position or the displacement, it is a property. In waves on a string, that property was a displacement. So here at open ends, the pressure does not change. Why? Because they're exposed to atmosphere. Because if you want to change the pressure there, you have to change the whole atmospheric pressure. Therefore, these are pressure nodes. Similarly, if you look at the particles here, these are free to move. There is no one stopping you from moving. This is like a free end. These are displacement antinodes. So you have to be careful, everyone. If someone asks you this question in an open end tube, what is an open end? Is it a node or a antinode? And then the question should be, boss, what are you talking about? Are you talking about displacement or are you talking about pressure? So if you talk about pressure, it's a pressure node. If you talk about displacement, it's a displacement antinode. Most of the time, we will study pressure nodes. Because if you put a particle there, there is no one to stop you from moving. So this thing oscillates freely without getting fixed. Therefore, this is a displacement antinode. Is this clear, everyone? Any doubts on this page? Now, if you think about with an analogy, doesn't this guy look like our regular sonometer? This is a node. This is a node. You can't tell the difference. Mathematically, they will look exactly same. Clear? So, how do you generate stationary waves on an organ pipe? So, you take an organ pipe, you put a tuning fork F. So, this thing sends waves inside. Remember, it's like a fixed end for pressure. This is the incident wave. It gets reflected. Then we get a reflected sound. So, what exactly happens, listen, just a little thing. So at an open end, whenever a compression comes, so what is a compression? High pressure region, P plus delta V max. Outside is P naught. So when this compression comes, what will happen? This is a high pressure, this is a low pressure, air will suddenly leak outside. Getting it? After leaking, it will start pushing the particles out. It won't stop when the pressure becomes P. Remember, when you take a pendulum and leave it from here, it doesn't stop at the mean position. It goes to the other extreme. Same way, as the pressure is decreasing, it becomes P minus delta P that gets reflected. So when a compression hits an open end, it becomes a rarefaction. I hope you remember, whenever you send a wave onto a fixed end, you get an inverted wave. Similarly, when a rarefaction comes and hits an open end, you have a low pressure region. So the atmosphere is more pressure, so the gas will rush in, pressure increases, and you get a compression. Is that making sense? So at an open end, when a rarefaction hits, you get a compression. When a compression hits, you get a rarefaction. It behaves exactly like a fixed wall. Again, think about this. In a fixed wall, what was not changing? The displacement of the wall. In an open end, what doesn't change? The pressure at the end. So if you look at that similarities, it kind of behaves like a fixed end. So if you look at the incident waves get reflected at the open end. Most people, what they think, sir, won't the sound just escape outside? Yeah, that's there. That some part of it escapes. Then the question becomes like this: we have a string and a thick string. Yeah, you always get a transmitted and you always get a reflected pulse. So we are taking an ideal situation where most of it is coming back. So incident waves get reflected at open end. Then this incident and the reflected wave superpose to form stationary wave. So the equations would look like this. So delta P incident. Again, I'm just writing a general equations. Because the wave got reflected, it is traveling in the opposite direction. When you add them, you end up with 2 delta P max. Sine kx cos omega t. I hope you can see the resemblance. They look exactly the same. And the amplitude is given by, again, we'll call this thing pressure amplitude. There. This is what I said. Mathematically, you can't tell the difference. Any doubts on this? Clear with this? And again, do you guys remember the general equation? What was the general equation? There. So this is what we did in the last class. So this is still valid. Any doubts on this? So what is the first possibility here? First possibility, you get one loop. Both the sides are nodes. Same story again. So this would be length L. The length of one loop will be lambda by 2. So frequency will be V by lambda, which is V by 2L. If you see, it is the exact same formula. The only difference is there V was root T by mu. Here V is root over gamma RT by M. This is the first harmonic or fundamental frequency. What is your second possibility? The second possibility, so the second possibility will be two loops. So L will be 2 times lambda by 2. We will get F2, which is 2 times V by 2L, which is 2F1. Second harmonic or first overtone. You can't tell any difference. Matlab, if I just show this equation, you can't tell the difference. So your general equation looks like this. So Fn NB by 2L, V will be root over gamma RT by M. N is the harmonics. Check it out. And this is what I said. If you had learned waves on a string properly, this thing you will find it straightforward. Clear with this? Now here, the one thing I used to get confused is, so in string, I told you these are different positions of the string. But in sound waves, you're still drawing the same way. So what the hell is this exactly? This is not the position of a string. So what we are drawing is, you're drawing, it's a graph between delta p versus x graph. So when you're drawing like this, I'll take one loop for simplicity. So at a distance x from here, the pressure is 2 delta p sine kx. So basically, this is a representation of pressures at every point. Here it is 2 delta p max. And this is your antinode. So this thing which I'm drawing here is actually telling you the pressure ka variations at that point. And what is the meaning of this side? It is minus 2 delta p max. So pressure is varying plus or minus 2 delta p max. Clear with that? So That means if you take a cylinder like this, and let's say I fill it inside with some propane gas or some, flammable gas, and then if I make holes here, right? And if I send sound waves and they form stationary waves, what do you think you will see? Wherever the pressure is low, the gas won't come out. Wherever there's a pressure, gas will come out, out. Here it will be more, then again decreases. Isn't this how the gas will come out? And if you light up a flame, then what will happen? You will see a fire like this, now. The thing is, we can't see the sound waves. But if you can send some gas like, flammable gas like hydrogen or propane, and if you put a fire, wherever there is more pressure, gas will come out with much higher speed. And wherever there is a low pressure, the thing will, what do you call that? It will not come out. So when you switch it on, you'll see a flame. Isn't this? So this is how it would look. I think again there's a problem with the audio, but let's see. Can you guys hear something? Okay, you can't hear. You can hear my voice, right? Okay. Okay. There's no audio for this, so let's see. I'll post the video anyway. So what this guy is showing you at the back, he has built a PVC pipe. On the right hand side, can you see there is a cylinder? That is a propane gas cylinder, and he made holes at every half inch. So every half inch he made a hole, and the gas is going in. Now, if you start sending sound waves inside, like I said, wherever there's more pressure, it will push out, and wherever there's less pressure, gas won't come out. And if you put on a flame, you should see your stationary waves. There. So there are no waves here. You can see the gas is coming out almost uniformly. Now, if you generate standing waves, can you see? I know it's not perfect, but you can see that's a fourth harmonic. Can you see approximate looks like a sine wave? So actually, this is what you do, pyrokinetics and all. Matlab, let's say if you have a rock band and if you put this gas and flame, and every time they play the guitar, even the flames dance with them. You can actually make their music. If you have a high pitch, the flame will be higher and everything. So you're playing the guitar and the flames are reacting to it. You're a firebender. Meaning, if you have seen Avatar. So this is the fourth harmonic. That's your sixth harmonic. So you won't find this in the labs because it is too dangerous with the gas and everything. This is also something similar. This is called Rubens tube. This is what I was saying. If you put music now, this is how it reacts. They're playing some decent disco. I'll send in the group. You can check it out with more audio. It feels better. But is everyone clear with this? So I can't show
Yeah.
you stationary waves of sound because we can't see sound, but we can see the flames. Clear with this? What is the second possibility? Second case. Open, closed. So the open end is a pressure node. This will be a pressure antinode. And why is that? It kind of makes sense. If you see at the fixed end, the particles are fixed. It cannot move. Therefore, it's a displacement anti-displacement node. Okay with this? So this thing, if you see, this thing kind of looks like a ring. If you remember this one, this is the second type of sonometer we saw. Exactly, you'll find again the equation looks same. This is a node. This is the antinode. So what is the first possibility? An half loop. Because this should be a pressure node and that should be a pressure antinode. This length will be lambda by 4. Frequency will be V by lambda. We get V by 4L. First harmonic or fundamental frequency. What is the second possibility? One and a half loop. This will be F3 is equal to 3V by 4L, which is 3F1. You can clearly see even harmonics are missing. Like I said, everything will look same. If you ask me, the only difference is the speed of sound curve formula is different. There it was T by mu and here it is gamma T by m. Check it out. Play with this. Any doubt so far? Anything not clear, not convinced, please ask. Clear with this? Now here we have a small problem though. We call it end correction. Now the thing is, even though we said open end is like, exactly pressure will be constant, in reality, when the air pushes through, right? Remember, there'll be some inertia. The wave suddenly cannot invert, right? It will push the atmosphere a bit, and then the node forms slightly outside. See, it is like this. Even if a cycle goes and hits a lorry at some distance, right? Even the lorry will move maybe in some centimeters or millimeters. So there will be always a small, displacement outside. So at open ends, the pressure node forms actually slightly outside. So it's not much. So this is how the equation will become. So the node will be somewhere here. This is given by E, which is end correction. And this is your length L. So basically, in place of L, you have to replace with E value there. So E is given by 0.6 times radius. Or 0.3 times diameter. Same thing. So your formula becomes this, everyone. V is equal to NV by 2L. It will become L plus 2E. Making sense? So basically, this whole length will be lambda by 2. Node to node is lambda by 2. So length plus 2 times end correction will be the lambda by 2. You just have to replace the length of the pipe with L plus 2E. Here there's only one end correction. Okay. And how do you have end correction? The biggest is this. So, but if they don't talk about it by any definition, because without that can't find it. Because this is an experimentally derived value. So that is the biggest clue. Whether to use end correction or not to use end correction. Clear with this? In this stationary vision and sound, we have two experiments which are again important. You will also get this in boards, you also get this in practicals, and advanced we have a separate topic called experiments. So this thing can be asked as a part of a sound waves or can be also asked as an experiments in physics. So let's say, and again, experiments are quite easy. But the thing is the terminology. If you don't know what they're talking about, the terms, it looks pretty weird. The first experiment is a resonance column tube. This is the schematic. So what is this exactly? This is an experiment to find the speed of sound. So I will just draw a rough sketch. So we have a pipe here. At the bottom, it is connected to a funnel kind of thing. And here beside this, you have a scale. So the idea is this: when you put water inside, you can't look like this and see how much water is there, right? So the idea is when you pour water, this water and the funnel will be at the same height, isn't it? If you put more water and push the funnel up and down, you can change the water level. The height of the funnel will be the height of the. This is a movable funnel which can be moved up and down. To measure length of the water column. Then what you do in the experiment, you take a tuning fork, then you send waves here and you get standing waves here. Let this be L1. So L1 will be the length of the air column. And that you can get by, subtracting the total length of the pipe from here. Is the setup clear? So when you move the funnel up and down, you can change the water level. We have a tuning fork of frequency. So how do we use this? So this is what we do. You can keep increasing the water level or you can keep decreasing the water level. Let's say we are doing the other way around. We keep decreasing the water level. Normally they keep increasing. At some particular length, we hear a sound basically. It sounds something like this. Matlab, you'll get a sound like no boom, the whole thing vibrates. You get a sound like that sort. So, and this keeps happening at particular lengths. So let's say L1 is the length of the air column. So this is what is actually happening. As you decrease in the water level, you got your first harmonic. This is your L1. But be careful, there is also an end correction. Then you keep decreasing the water level, the sound goes off. Again, you will hear a boom sound. This will be L2, this is E. So from here we can see L1 plus E will be lambda by 4. L plus E will be 5 lambda by 4. When you subtract them, L2 minus L1 will be lambda by 2. You know, start from the top. You can start even from the bottom also. You can keep pouring water. So the wavelength, the distance between two consecutive columns will be always lambda by 2. And the best part, right? The end cursion gets cancelled automatically. Then you're done actually. That means lambda is 2 into L2 minus L1. Therefore, speed of sound C will be F into lambda, which is 2F L2 minus L1. There you found the speed of sound. It's a pretty easy experiment, but got the logic there. You hear a boom sound. It doesn't matter at what length it happens. When the second one happens, the difference in length must be always lambda by 2. So clear with this? And once you got the length, from there you got the lambda. Once you got lambda, you already know the frequency and you're done. The experiment is pretty easy. But what I saw now, people get confused. Questions में ऐसा होगा. What happens if the radius of the the resonance column is changed? What happens if the temperature is changed? People don't understand what is a resonance column. Like I said, it's more with the terminology than the experiment. But is the experiment clear, everyone? Any doubts? Anyone not clear with anything? Please ask. All clear with this? Then the second experiment is Kond's tube. This is also experiment to find speed of sound using stationary waves. This would be the schematic. So what is this setup? I'll give you a rough picture. You take a cylinder. Let's say this is fixed. This is a movable piston through which you can change the length. Then what you do, you put some powder inside. Now tell me one thing. Whenever sound waves form, you'll have displacement nodes and displacement antinode. What is the meaning of displacement antinode? The particles at displacement antinode will oscillate up and down with a large amplitude. So the powder particles at displacement antinodes will start flying up. will fly and get accumulated at nodes. Why? Because at nodes the particles will not move. So whatever powder falls on the nodes will stay there. That means when you generate stationary waves, this is how the picture would look. So you will actually find heaps of powder like this. And these points will be displacement nodes because the powder at the nodes will not move. And then what we do, we measure the distance between the two hills, or we actually measure the distance between the two gaps. This would be lambda by 2, isn't it? Because distance between node to node is lambda by 2. And then you're done, same story. You know lambda, so speed of sound is equal to f lambda, you get the speed of sound. So this is kind of like Rubin shoot the fire wala thing, but without fire. It's more safe. Is this making sense? And how does this look like? There's a bit of a lag, but listen, this is a little different than what I just told you. Here, what they did, they didn't keep powder. What they had, this small pieces of paper attached at the bottom. Okay, now the particles can't fly away. So wherever there's an anti-node particle, this will fly higher. Wherever there's a node, these particles will not move. Right? Why is there so much lag? It was working till now. You can clearly see it's like a Kunst tube. You have a frequency generator on one side. Can you see that? You can see that hump. So the thing here is, like I said now, here you're not keeping powder which will fly away. You are actually taking papers and small cloth pieces, thin pieces. They're attached at the bottom, so they can't fly away. So at antinodes, they will fly higher. At nodes, they won't fly. There, that's your one loop, 119 hertz. Second harmonic, two loops. So there is a better one than this. So look at this plate. This is actually a Kunst tube in 2 dimension. I'll just explain you what is the setup. You have a plate. Okay. At the bottom, you have a frequency generator. Now here, the waves are going front and back. Waves are also going left and right. So you're actually creating stationary waves in 2 dimensions. Okay. Now what this guy is going to do, you're going to put some salt or some kind of a sand on the whole thing. Now when this plate starts vibrating, wherever there is a node, what will happen? The sand will get stuck. Wherever there's an anti-node, the sand will start flowing away and they accumulate at the nodes. Now, because it is a 2 dimensional, you will actually find a kind of a pattern. So observe that. Can you see how it looks? So this is 345 hertz. So that entire thing which you're seeing is a 2 dimensional node. इसको देखे कुछ याद आ रहा है? Bohr's theory, stationary waves. If you put more salt and more frequency, this is 1033. So in case in your society, if you have a Rangoli competition, you can keep this. And if you just change the frequencies and the Rangoli keeps changing, you have made an infinite Rangoli thing. And you can go further. This is 1820. You're getting, and this just keeps going on and on and on. I'll post this video. You can actually see this with sound. It feels good. You get really good patterns. Yeah, this is 5201. And again, like I said, if you keep increasing the frequency, wavelength decreases, you get more loops. Clear with this? There. So that is the complete theory of stationary waves, right? And I think next class when we catch up, we will do problems. We'll wind up with that. I think my net is also lagging a lot for some reason. Certainly. Okay. Then, like I said, last time